So I couldn't resist going from this slide to the acronym version. There's so many acronyms today. I had to jump to ICCS. We've been going about a year, so I'm mostly going to be telling you just about the sort of the background, motivation for the Institute, rather than sort of results, but going to give you an overview of what we're up to. Now, I think it's worth just going back to the beginning and the starting point of the Institute. As we all know, the Earth is warming. Average global temperatures have been rising above pre-industrial levels quite significantly recently. And through the works of climate science, climate modeling, we're pretty confident that this rise is due to it's due to ourselves. It's anthropogenic, rather than some kind of internal variability. There's still a lot of work to be done in climate science, in understanding how all this complex machinery of the Earth system works together, how it's impacted by our activities, and how its changes as we go forward are going to impact our activities. So climate science is ever trying to understand more and more about how the Earth system works as a whole. And one way of doing this, of generating higher fidelity predictions, is that you want to increase the resolution of your models. So you start off with your differential equations, your PDEs describing fluids, and you do some numerical analysis, you discretize them down to get a discrete approximation, you represent it as matrices, as arrays, and to get higher precision predictions, you increase the resolution of those. So this is a representation from the fourth IPCC report that shows the sort of increase in resolution over the years, and sort of weather models tend to be even higher resolution to get better predictions. So this is one way in which we can improve our forecasting and predictions understanding of the Earth system. Another way is to increase the complexity of the models in terms of the number of processes that are involved and the way they're interconnected. So not just temperature and CO2, but adding in other bits of the weather, clouds, rain, surface, ice, oceans, activity of volcanoes, industry, carbon cycle, and so on. There's a huge amount that can go into these things. So really what's going on is sort of scaling up across two axes here. And Jules Charney, who was one of the kind of founders of climate science, working very closely with John von Neumann, once they had computers, they started saying, great, we can do numerical weather prediction. And he talked about having to climb this ladder, this model hierarchy, having more and more processes and higher resolutions. And this is the way to get more understanding of the way our climate and Earth system works. So for the purposes of this talk and explaining some of the things that we're looking into, I'm going to suggest that this activity, scaling up, going along this ladder, actually breaks down into three other kinds of scaling across some other dimensions which are not necessarily orthogonal. Actually, they're kind of highly interrelated. And you've got to have some kind of pithy alliteration. So that's computation, collaboration, and communication. So these are the ladders we've got to climb to sort of improve our understanding, but unfortunately the ladders are missing some rungs, and those are the challenges that are faced that we're trying to address in our institute. So focusing on the first, the computation part, as we add in more processes and we increase the resolution, we need to spend more time computing. We need to use more computer cycles. And in the past, say last millennium, we could just wait for a bit of time, about 18 months to 2 years, and buy a new computer, and that new computer would be faster, and we could run the model that we had a couple of years ago, and it would now run faster, so we could dial things up, increase the resolution and the processes, and everything would be great. You basically wait a bit of time, and you can do more. And this was partly due to a scaling trend, two interrelated scaling trends known as Moore's law and Dennard scaling. Basically, every 18 months to 2 years, the number of transistors that you could fit on a piece of silicon was roughly doubling. The smaller you make them, the faster you can clock them, and you could keep the power density the same, so you could get more performance, basically, as time went on. And that's kind of represented by this green set of data over here, going up, but then, oh dear. Sadly, around the 2000s, it starts leveling off. You can see that in the blue as well. This is the performance of a single core on a processor. It starts leveling off. So we started sort of hitting some physical limits in our ability to make things smaller and deal with leakage of current and things like that. But we've still been able to increase the number of transistors. So a sort of industry solution to try and still squeeze out lots of performance of the processors is to increase the number of cores. And so, this computer has 10 cores, this phone has 4 cores or something like that. And so by parallelizing our software, by running computations concurrently, we can squeeze out some more performance, but that requires us to re-architect our systems. Now, in climate science, for a long time, we've been exploiting parallel hardware. The supercomputers of the 70s and 80s were kind of testing ground for that. There's lots of techniques for doing that, but it requires a lot of re-engineering effort to exploit the parallel architectures that we now have available. And we're no longer in this nice kind of lovely era where we could just wait a bit, buy a new computer, and get more performance out of it. The computers now are getting bigger, but they're not getting faster. So one impact of this is particularly felt when we start thinking about what happens below the minimum resolution that we can deal with. These are so-called subgrid processes. So there are lots of Earth system processes that are really, really important for understanding how things work as a whole. Things like clouds and ocean eddies, these kind of walls that happen in the ocean, and they're big transporters of energy, heat. But often they're at the level of, say, a kilometer or less than a kilometer, so much lower than our minimum resolution, but they have a really big impact on the overall system. So one way to deal with this is by these approximate models that happen below the minimum resolution. They're called subgrid closures or parameterizations sometimes. And this is known to be a source of quite a lot of uncertainty in the models, or at least sort of differences and divergences between different models, because people make different choices in the way they build these approximations. Or you could just spend a lot more computational resource and sort of dial up the frequency of your fluid dynamics simulation to try and sort of squeeze these things out, but it's just become too expensive. But there's been this really interesting trend, which is particularly relevant today to C2D3, of looking at these and realizing that we can actually replace these subgrid closures, these subgrid models, with machine learning techniques. So we can take a lot of techniques have been developed in kind of computer science, AI communities using neural networks, typically convolutional neural networks, and train these neural networks either on a very high resolution and expensive model or on actual real data, and have this drop-in replacement for our previous subgrid models that goes in place instead here. And this has been done, and there are many different kinds of models for different processes, but we're discovering that this can have very good predictive performance and can also be computationally cheaper than the previous subgrid models that have been used or the higher resolution models. People then joke that this is kind of like climbing down Charney's ladder, because in the past, in the 19th century, if you wanted to do weather prediction, what you did was you sort of took your measurements of the pressure and the temperature and the wind, and then you got out your big load of charts from the drawer and said, okay, what's a chart that roughly looks like where I am now? And you did pattern recognition. You found something that matched, and you said, well, last time we had this kind of pattern, then this thing happened next. And that's kind of what's happening in a neural network, right? It's learning patterns, it's a big pattern recognition tool. But then we lose a bit of the explainability. We lose this understanding of what's actually happening. It's a bit of a black box. So working explainable AI and human digestible AI outputs is then really important here to actually help us still do science where we actually know what's going on, rather than just, well, we trained this thing to do pattern recognition and it said this was going to happen. So lots of exciting stuff there. You can still use these things and train them on different variables and sort of look at how much the different components affect this particular weather source and learn that way and do science that way. But there's still a lot to be said about trying to explore the explainable AI component. And then there's a bunch of technological challenges that come around this. So I use PyTorch or TensorFlow or something like that in Python to build one of these models. But what I want to do is then go and take it and plug it into my large general circulation model, which is written in Fortran and is about 500,000 lines of code. There's some interoperation that you have to do, but you want that to be as performant as possible so that you're not wasting a bunch of time moving data between different language runtimes. So that's something that we're looking at with a number of our science teams, getting that to be as efficient as possible. So along with the idea of adding more and more processes into our models, then comes more and more collaboration between different scientific groups who are focusing on different things. And then you get to this human problem of how do you scale collaborations, and particularly when it comes to writing big pieces of software, which is what climate models are. The model is the software. And then you sort of hit what I like to call the two complexities of scientific code. There's the inherent complexity of all of these interacting non-linear processes, and then there's the accidental complexity, which comes from like, oh, well, we use this discretization, and we've optimized it in this way, and we use this library and this version and this optimization technique, and these kind of obscure each other and make it very difficult to do effective software development, and can also make the general collaborative effort difficult as well. I'll come back to this accidental complexity in a moment. So fortunately, in the field of software engineering, there's been a lot of work into thinking about how large teams of people work together on a common piece of software, and as has been mentioned a bit before with things like in the Alan Turing Institute, there's a lot more use of these software engineering techniques now in climate science. So that processes, sort of development processes like the agile methodology, tools and systems like Git for managing large amounts of source code and the collaborative editing of it, build systems and containers to help you deploy things more easily. I don't have fancy graphics for these ones, but debugging tools, profiling tools, things to help you analyze the software that you're producing. And a favorite of mine is also testing and verification. To make sure, does this thing do what I want it to do? What are the bugs? Is it free from bugs? How are we actually going to understand if we're optimizing it, whether it has the same behavior? And this is something that I have a tool that I work on with a number of people called CamFort, which is a static analysis tool for Fortran that's targeted at scientists, trying to find sort of the sweet spot for sort of helping scientists analyze their code and understand how it behaves at a higher level. So there's a bunch of structural and cultural change that needs to come along with these things, because climate scientists not typically trained in all of these things. It's sort of something that people tend to learn as they go, but there are tons of things going on all over the place to help train people in these areas, which is very exciting. Something I think is great, that I've been involved in for a while, is the Software Sustainability Institute, which is sort of this UK-wide, UKRI funded, or EPSRC funded, institute to support the role of software in all kinds of research and support those people who are trying to raise the level of software engineering best practice in their community. Now, this great slogan, better software, better research, kind of crisply captures that idea. Then there's been the rise of the concept of research software engineers as this really important key role in science that is now sort of fundable directly and is recognized finally as an important part of the scientific process, and nice resources like the Turing Way and so on. So there's great stuff going on there, and we're involved then helping train scientists and helping embed these processes into what they do. And the last thing, which I think is a bit more speculative, so I'll spend a bit less time on, but is this idea of scaling communication. So you're sort of scaling up your teams, and we want the science that we're producing to have maximal value beyond the life of our project, say. And so how do we do that? Well, we write papers, right? We like writing papers and publishing. That's great fun. It's a great game. And that's one way of communicating amongst humans. Another way that we do that is by writing code. Now, you might think, oh, well, code is for communicating with a computer. It's how I tell that thing what to do. But it's also a tool for communicating amongst humans. And when you get very, very complex models, like in climate science, the papers don't have all of the information you need to reproduce the science. The code has what you need, but then it's all mixed in with this accidental complexity as well. So it's kind of this problem where in the papers, you've got the abstract model and maybe something about the solution strategy, and then in the programs, you've got more of this side, the prediction and the calculation, but it all gets kind of smushed together in the code. It's very hard to pick apart. And so there's this kind of gap between papers and programs. If you give someone your source code, that's great. They can now repeat the calculations, maybe once they figure out how to build it and deploy it and so on, maybe they can repeat it, but can they actually reproduce your science, make their own model, reproduce your conclusions, even if they don't get the same numbers? It's very hard to do because of this gap. The papers have the high level, the programs have the low level, and a lot of things conflated together. So sort of dealing with this gap is something that I spent time thinking about. You can sort of go some of the way with maybe a clear systems design, more documentation, modularization. But I think there's a lot of unexplored stuff, thinking about how you can actually have languages that help you do that, help you bridge the gap between the abstract and the concrete. And it's very hard to make new languages and get people to use them. So this is a difficult thing to think about, but great progress with things like Julia. That's a new language that's broken into the space, which is kind of exciting. And so I think there's something to think about for the decades ahead about how we have languages that support the scientific process. So these are the three different dimensions of scaling that then are involved in making progress in this area. And so we're sort of attacking this from a variety of different directions. And so we've got lots of different people involved from across the university. So this is the directorship here. You can see we all come from different departments. Emily from computer science, and me from computer science, and then Colin here at DAMT, Chris Edsel, who's the head of research software engineering, and then Marla, who's our program director, and she's here if you want to talk to her later. And so we're bringing together all of these different disciplines to support climate science, and we see that there's a lot of work in all of these disciplines that can really help support climate science going forward, and there is already interaction, but we want more interaction of all of these things going in to help the climate scientists. We're very grateful for Schmidt Futures, from whom we've got our initial funding, and they launched this really interesting thing called the Virtual Earth System Research Institute, where they're funding lots of large climate science projects that cross many different universities and lots of different different bits of climate science. So one of the things we're doing is directly supporting them. So these are the 4 projects that we're working with, do lots of interesting different things. So we have a team of research software engineers, these fine people over here, based in Cambridge, who are working directly with those teams. And then from that, we also look at some of the general kind of cross-cutting concerns and research questions that come out of that. Think about, there's lots of sort of cross-cutting things that happen amongst the teams, especially in the use of AI. And we have a research stream as well with some postdocs, advanced postdoctoral fellowships. And Laura's recently started, and we've got 2 more we're hiring for. So across the teams, there's a lot of these data-driven techniques, and we're seeing that that's an increasingly important way of getting over some of these scaling issues to produce better science. Okay, so if you want to know more, you can check out our Twitter and our webpage. And also a little plug, we're running the Climate Informatics Conference in Cambridge in April. So if you're sort of interested in or want to know more about the intersection between climate and machine learning and AI, then please come along to that. It will be here in Cambridge then. Okay, thank you.
Thank you very much, Dominic. Bit of time dilatation there. So